Hi students, welcome. This is Chemistry Chapter 6, Section 5, Part 2 lecture. We will be going over this in class. I have a handout that will show all this VSEPR theory as to the bond shapes, and you will be allowed to use this worksheet upon your exam that we'll be taking here pretty soon. Anyway, this section begins on E, VSEPR, and unshared electron figures, and it asks you to take a look at figure 6-22. Number 1, NH3 and H2O have centralized atoms that have both shared and unshared electron pairs. Number 2, group 15. NH3, the N has 3 electron pairs to share with 3 hydrogens. Under A, the lone unshared pair occupies around nitrogen just as bonding shared pairs do. B, the shape name refers to positions of atoms only, not unshared pairs. Under C, figure 6-22A, if you could please take note of that. This is where we would draw it at. The bond angle is equal to 107 degrees and trigonal pyramid shaped. That's trigonal, T-R-I-G-O-N-A-L, pyramid, P-Y-R-A-M-I-D, shaped. The form is AB to the third and E, where E represents the unshared electron pair. Number 3, group 16. H2O, the O has 2 electron pairs to share with 2 hydrogens. Under A, 2 unshared pairs are found around oxygen and 2 shared pairs with 2 hydrogens. Under B, figure 6-22B. You need to be able to draw that. The bond angle is 105 degrees and it is called a bent Tor angular shape, B-E-N-T-O-R A-N-G-U-L-A-R shape. The form is AB2E2. Number 4, bond angles for water and NH3 are less than 109.5 tetrahedron because the unshared electrons repel the electrons more strongly than do bonding electrons. Number 5, table 6-5 includes a AB2E example is SnCl2, where Sn is the central atom, forms 2 bonds, and retains 1 unshared electron pair. Number 6, double and triple bonds are treated same way as single bonds. Polyatomic ions are treated the same as molecules. Number 7, the Lewis structures in table 6-5 can be used for polyatomic ions and molecules with double and triple bonds. We will do then sample problem 6-6. We're going to predict the shape and draw CO2, predict the shape and draw ClO3, and then we will practice. Continuing on with F. Hybridization. Just like the word hybrid means, that means we are going to be combining some traits together. Kind of like hybrid corn. We combine traits of corn together to produce a variety of corn that would grow very well here in Iowa. This is hybridization. Number 1, the VSEPR does not reveal relationships between geometry and orbitals occupied by bonding electrons, so a different model is needed. Number 2, hybridization is a mixing of 2 or more atomic orbitals of similar energies on same atom to produce new orbitals of equal energies. Number 3, methane. CH4. The C atom has 4 valence electrons, 2 in the 2s and 2 in the 2p orbitals. Experiments show that methane has 4 equivalent equivalent covalent bonds with tetrahedral shape. The question is how? Number 5, the carbons 1s2 and 3 2p orbitals hybridize to form 4 new identical orbits called the sp3 orbitals, where the 3 indicates 3p orbitals and 1 implied s orbital were used to hybridize. See Figure 6-23. Number 6, hybrid orbitals have more energy than 2s but less than 2p. Number 7, hybrid orbitals are orbitals of equal energy produced by the combination of 2 or more orbitals on the same atom. Methane, Figure 6-24a. Number 8, hybridization also explains bonding and geometry of group 15 and 16 elements. Figure 6-24b shows NH3 and Figure 6-24c shows H2O with 4 sp3 hybrid orbits between all shared and unshared electron pairs. Number 9, BeF2 really has a linear, linear shape due to hybridization involving the s orbital and 1 available empty p orbital to yield an sp hybrid orbital. Number 10, BF3 really has trigonal planar shape due to hybridization involving the s orbital and 2 available empty p orbitals to yield an sp2 hybrid orbitals. Number 11, and this is very important, Table 6-6 summarizes the 3 types of hybrid orbits found on page 189. And this concludes our lecture for Chapter 6, Section 5, Part 2. Thank you very much.